All right, this is Dr. Joseph Hagmann. He is a renowned quantum materials researcher in the past, and now is still a quantum materials
I still
researcher,
consider myself.
but with a bit of a cherry on top, as he's at MITRE, and so it lets him do things at a little bit different scale than before. So I think you're going to be telling us about that.
That's my hope.
All right, that's my hope as well. So take it away.
So thanks for the introduction. Thanks for inviting me here. It's an honor to be part of this discussion with all of the other speakers that you've heard and will hear. I'm Joseph Hagmann. I'm at the MITRE Corporation. My background is in quantum physics and materials, so understanding the quantum phenomena hosted in some of the materials you've actually heard talked about here, two-dimensional materials, among other things, to understand how we can exploit those quantum phenomena for new technologies. So I spent 8 years at the National Institute of Standards and Technology trying to understand how we can use those materials and the phenomena that they host for exquisite measurements. And so the last 3 years I was there was to measure the volt, because that's what the National Institute of Standards and Technology largely does, is it measures the fundamental measurement, the fundamental constants, the SI. So now I work at the MITRE Corporation. And the MITRE Corporation is a not-for-profit organization that administers federally funded research and development centers. And it does this to solve whole-of-nation problems. So I'll talk about what we do at MITRE, what MITRE does, and broadly what we do in the quantum research space. So you've heard people talk about both ends of quantum research. You've heard about the very basic research of materials and phenomena. And you heard from George Thomas about the quantum ecosystem and sustaining an environment where quantum research can thrive. Within there, you heard about N5 sensors doing research towards an actual sensing applications. And so MITRE exists to somewhat be a connector between all of these, similar to what the Potomac Quantum Innovation Center does, with a little bit more of a specialization of finding emerging technologies and shepherding some of them across what is called the Valley of Death towards useful application. And the Valley of Death is this concept of, we have funding for basic research. And we, as many of you know, and work with the faculty who do this kind of work, are extremely good at doing research for discovering new physics and understanding the physics of our universe. And then we're really good at taking things that can make money and commercializing them and marketing them. There's this gap in the middle where it's really hard to fund things that work in principle, but may not actually be commercializable or useful in real world situations. And so it's many of the people with money are hesitant to invest in this space between discovery and commercialization. And it's there where innovation can happen if you are prudent about finding which of those emerging technologies are worth shepherding across this valley of death. So we have a way of doing that at MITRE. Let's see. Yeah. So I'll talk about, first I'll talk about some of the quantum technologies we think about. Quantum technologies, one of the famous ones is quantum computing, which is able to do certain types of algorithms that can solve linear problems much better than a classical computer, which means that it can break asymmetric cryptography. This is something you'll hear a lot about, is that a quantum computer makes your RSA tokens worthless. It makes your Bitcoin wallet hackable, right? It's that it can break asymmetric cryptography, and that has consequences on digital security. It can enable efficient machine learning. We can solve problems better. We can actually do simulations for material and drug discovery, because when you want to simulate a quantum thing, it's nice to have a quantum computer actually do that. So quantum computers are a hardware accelerator for computing things that classical computers are not necessarily the best at. And that's going to open up a lot of, I think, new opportunities. There's billions of dollars going into quantum computing. And as a consequence of their ability to break asymmetric cryptography, there's lots of money going into what do we do about cryptography when quantum computers can break them. So this is actually not a field of quantum research. This is a field that arose because of quantum computers. Researchers are developing alternate asymmetric cryptographic schemes that are robust against the attacks of a quantum computer. So in spite of that not being quantum per se, it still exists within the quantum ecosystem as a consequence of the one-day emergence of quantum computing. Two other quantum technologies are quantum communications and quantum sensing. Quantum communications is somewhat related to quantum computing and more so related to quantum cryptography because it enables end-to-end encryption where you can encrypt every single bit of data rather than bulk encrypting using the schemes that we know now. You can actually just encrypt using one-time pads every single bit of data and provably securely, which means if somebody were to tap into your communications network and eavesdrop, by virtue of the quantum physics of the mechanism used for this communication, the two people communicating with each other would know that they are being eavesdropped on. They can cut their communications to prevent further leakage of their data. It can also be used for enhanced clock synchronization. And then the final one, which is the kind of things I work on now more than anything else, is quantum sensing. And there are many quantum sensors I'll talk about, but there are various sensing modalities that exploit quantum phenomena for, and I'll talk about this a lot, things like smaller size, weight, and power, and enhanced performance. And so in the context of that, one of the things that we think about at MITRE is not just can these things work, can quantum technologies work? We have to think about how they will be used and who will use them. And the answer to that is usually people that do not care about the cool physics. For them, it is a black box. It is a technology that they plug in and they need it to work. And they're comparing it with non-quantum technologies that may work fine. That may work fine when you have to account for power consumption or account for price, for complexity. And so quantum sensors, when we think about them, we want to identify the ones that are going to be smaller, way less, perform better, or consume less power within some combination of those things. And I think missing from this list of quantum technologies, Patrick, quantum materials, I'll have to figure out how to incorporate that into my slide
right. They're
deck.
not a technology to themselves.
But they're an enabling platform.
They are the enabling of all.
Hey, as I go, this can be conversational. If anybody wants to ask a question, stop me. And we can have the questions come up as we're going, as opposed to all at the end. So I don't have to scroll through the slide deck to answer the questions. So feel free to ask questions as they arise. So there's a lot of words, but generally what we do under the federally funded research and development model is we solve whole of nation problems as they relate to emerging technologies, in this case, quantum. And part of that means doing the research ourselves. We have a bunch of PhD physicists and master's physicists and bachelor's degree with a lot of expertise in technical work, working on actual quantum sensors. They're also working on understanding the problem spaces of MITRE sponsors, the people that fund our federally funded research and development centers. And so we're able to take both hands-on knowledge and application knowledge and blend them together to answer the questions of what are the emerging technologies, who are the companies and researchers operating in those spaces and developing those technologies, and which ones can actually solve problems that require exquisite sensitivity or low power, and identifying which of those emerging technologies should be invested in so that we can shepherd them across the valley of death towards real world applications. So a combination of understanding the basics of the physics, the integration into a sensing or computing technology or information processing technology, packaging it up, and then delivering it for fieldable use. That's what MITRE thinks about, the whole chain of systems engineering. So You've heard a lot about quantum technologies already. I'll just run through them quickly. We've heard a lot about quantum computers, and you'll hear a lot more about it tomorrow. But effectively, they are hardware accelerators that can compute things, certain things, better than classical computers. So the top left, you can use quantum amplitude amplification to run an algorithm called Grover's algorithm, which lets you sift through unsorted databases to do things like you can actually attack symmetric crypto systems. So this is the AES systems. This is when you do TCP/IP, your link to the computer. When you have HTTPS in your browser, you have a symmetric encryption going on. Grover's algorithm ostensibly can break that, and it is considered that the best case scenario is that it can do so about twice as well as a classical computer. Also, you can use this for quantum machine learning, and effectively you're more quickly sifting through data. The big thing we often hear about is how Shor's algorithm can break asymmetric encryption. Other things it can solve linear equations very well, meaning you can do linear algebra to do machine learning and AI. You can use it for novel material and drug discovery. And again, that's because if you want to simulate a quantum system, you can use a quantum computer to do that. And finally, there are things called quantum annealers, which can do certain optimization problems, but they don't have the full suite of gates to do universal quantum computing. So they're really good for certain optimization and logistics problems. Quantum computers pose threats, and they provide opportunities. I'll just quickly through this. Quantum computer leverages these aspects of a qubit superposition, so that a qubit is not just in a 1 and a 0, it is in a combination of 1 and 0. And it's not just a combination of 1 and 0, there's actually a phase term. So you can almost think of it as an arrow on a ball, inside of a sphere. And that arrow can be pointing up as a 0 or down as a 1. It might be 0 is down and 1 is up, whatever. But it can also point anywhere around that sphere. And that's the information that's encoded in a qubit. And then you can take a bunch of those qubits and link them together so that you can have a highly paralleled operation from which emerge answers to questions you pose to these algorithms. Again, that can give you answers more quickly than a classical computer, serially proceeding through gates of operations of zeros and ones. So something that's important to know about quantum computers is that a lot of the promise is premised on the availability of a universal fault-tolerant quantum computer. It needs to be able to do these operations without a bunch of errors. I'll point out later on when we talk about how MITRE has come up with a suite of benchmarks that include both the number of qubits, but also incorporate error rates. You can have all the qubits in the world, but if they're accumulating a bunch of errors as you perform your computation, your answer is going to be wrong. It's not going to be very useful. So much of the work in quantum computing is dedicated to solving the fault tolerance problem. And, if anyone figures that out, they are going to be heroes of the quantum ecosystem. Post-quantum cryptography emerged because of the threat quantum computers on classical cryptography. NIST is standardizing a new suite of cryptographic schemes that are not threatened by quantum computers. So quantum computers can do the discrete logarithm problem for RSA or the elliptic curve cryptography problem. We can solve those problems fairly straightforwardly in an amount of time that would make it reasonable to attack those cryptographic schemes. But these other schemes, like lattice-based cryptography or hash-based cryptography, are not susceptible to quantum attacks. And so these asymmetric cryptographic protocols are already being implemented, or at least they're preparing to implement them as soon as NIST finalizes the standardization. Many companies are already starting to prepare for this post-quantum cryptographic future that would allow for a continuation cryptographic security, even with fault-tolerant quantum computers, because they wouldn't do anything useful. They wouldn't do anything more more capably to hack these algorithms than a classical computer would. So again, you get sort of these concepts of no one could hack these cryptographic schemes within the lifetime of the universe, which is one of the things that people say about RSA right now. Quantum communications. This is a lot of words to say what I've already said earlier, is that quantum communications can allow for quantum information to be communicated from one quantum node to another far away to exchange quantum information or a metal entanglement over a long distance. But for communications, this is largely to perform very virtually unhackable form of encryption called a one-time pad using quantum key distribution, which allows you to flip bits encryptedly with encryption and spot if somebody ever were to, if a hacker or an eavesdropper were to listen in on your conversation. So quantum sensing, this is the last one of the four. You can measure, you can use the qubit instead of using it, isolating it from the environment, and then carefully performing gate operations, which is what it's done, which is what is done in quantum computing. Instead, you allow your qubit to interact with the environment and use those interactions as your gate. So the interactions of the qubit with the environment are going to change the quantum state of your sensor, and you can exploit that to know what it is that you're sensing. You can exquisitely measure magnetic fields, electromagnetic fields, and electric fields. You can measure inertial acceleration. You can take an inertial accelerator of cold atoms and throw it down a mountain, and then, well, maybe not throw it down a mountain, but maybe I don't know, move it gently on a cart and measure its acceleration by the change in phase that accumulates along with the direction of acceleration of a moving beam of particles. And you can measure gravity by that same effect. In time and frequency, we call atomic clocks quantum sensors in this paradigm because you're using it's actually you're measuring quantum oscillations in cesium atoms or rubidium atoms, using that to measure time. You can actually also use these to measure gravitational fields, because if you move the clock far away from Earth, it's going to oscillate at a different speed than if you kept it close to Earth, due to, actually, it's going to be in orbit, so it's going to be a combination of both special relativity and general relativity that we're able to measure with atomic clocks, since they're so precise. So MITRE's work in quantum technologies. We develop quantum sensors in the modalities in yellow. So we do magnetic field sensing with solid state effects. We do electric field sensing with Rydberg atoms. And we've just started doing electromagnetic detection with superconducting sensors. And I'll talk about the first two of those. We've only just gotten started with superconducting sensors. But the way we do quantum sensor R&D is that we leverage the physicists that we have on staff and the knowledge that they have. We work with signal processing and RF and electrical engineers to take the quantum thing and actually turn it into a little widget that you could stick on an airplane or on a bicycle or in a headset. And then we work with operational analysts, people who understand the needs of MITRE sponsors, to know what are their power consumption limitations, how robust do these things need to be. So an example of this is some of the field tests will include taking a new device, a little widget, and bringing it out to a field and putting it on the ground, kicking it, burying it with rocks, and pouring sand over it. And if your device can't survive that test, then it's not useful in that operational environment. If it can't survive the trip into space, it's not useful on a satellite. If it can't survive cosmic rays smashing into electronic components, it's also not useful in a satellite. So it can't just work. It has to work in pretty nasty places, or even anywhere outside of our benign laboratory environments. And so we think about that when we do our quantum sensor research. So I'll talk about two things: the Rydberg atom field sensors and our quantum diamond microscope. Starting with the Rydberg atom sensors. So our internal R&D is, in this case, is focused on a quantum sensor that can replace antenna for electric field detection for communications. And the cool thing about this is antenna have to be about the length of the wavelength they're detecting. So if you want to detect very long wavelength radio waves, you need a really long antenna. But in this case, you will only ever need a vial of glass about this big as your, I'm going to use antenna for lack of a better word. The people who work on this don't like calling it that. Maybe aperture. So you get a small size antenna that's eminently tunable. The tunability is from kilohertz all the way up to almost terahertz. You can sense within that entire range. We're doing experiments down here in the lower frequencies, but the best projected sensitivity is at these much higher gigahertz frequencies. So small size, broad tunability means you have gigantic spectrum awareness in a small vial. And so this is based on a Rydberg atom, which is a alkali element. And you pump it with blue light and then red light to excite the outermost electron way, way out. I mean, this thing is a big atom. I think it's macro size when you do that with a rubidium atom. And so you get what's almost like a gigantic hydrogen atom, where you have one electron on this far out orbital, and the rest of the atom is positively charged. So you get this very, very big sensitive dipole, which is what allows for this RF sensitivity. The other project we're working on is a quantum diamond microscope. And this is based on nitrogen vacancy center defects in diamond. So we learned from previous talk on defects in silicon that defects can be problems in certain semiconductor situations. They can be utilized for or exploited for transistors. Transistors, we purposely put defects into transistors to get certain characteristics that let us use them as switches or as amplifiers. But in this case, we're using them as a detector, as a molecule that's hosted in quantum lattice that lets us detect magnetic fields through a fluorescence measurement. We shine a green light on these nitrogen vacancy sensors, centers in diamond, and they emit red light. And the amount of red light that they emit is going to be a function of two things: a microwave frequency that we apply to the diamond. So we shoot a microwave frequency radiation at it, and the frequency of that plus the amount of magnetic field, the magnetic field. Let's see. The amount of magnetic field that it's absorbing or that it's experiencing in the X, the Y, and the Z directions, or more specifically along the crystallographic axes of the diamond, is going to tell us information, vector information about the magnetic field, meaning we can, and it's doing this in a way that we can measure with a camera. We can sense this with a camera. So we can spatially resolve magnetic field information with nearly sub-micron level resolution on the orders of tens of nanometers in a matter of milliseconds. So we can spatially resolve very quickly magnetic fields, which means that we can watch integrated circuits working. And what that allows us to do is detect aspects of integrated circuit operation that is undesirable. So the introduction of Trojans for leaking cryptographic information, or the detecting counterfeits. So there's a big problem in the electronics community where if you buy an electrical component, rather than getting a new one with a well-known lifetime of that component, there is an entire industry around taking old components and then chopping them off of circuit boards, fixing them up, and selling you old counterfeit electronics components. And you'll buy them thinking that you have a good, fresh IC, and it'll die in a couple weeks because you bought a counterfeit one. This is a tool that we use to detect counterfeits, to detect faults in circuits, integrated circuits, and printed circuit boards, and overall use it as a tool for maintaining integrated circuit hardware security. So we do this in collaboration with academia and industry to develop a quantum sensor that we think can actually assure our microelectronics industry. Our role in quantum computing is a little less hands-on. So we're a neutral arbiter for evaluating quantum computing, trying to come up with more realistic benchmarks that allow for forecasting, beating down hype cycles. And one of the difficult things about hype is that hype brings in investment, but too much hype that is not met actually results in a steep drop in investment that can actually kill an industry. So if we hype this up too much falsely and investors don't like what they're seeing and pull all those investments at once, we could end up with what's called a quantum winner. Now, I, for one, would like the quantum ecosystem to maintain its viability and the investment into it. So one of the things we do is we make sure that the hype doesn't result in a quantum winner, in a depletion of investment into quantum, by making sure that the hype is appropriate and forecasting appropriately the usefulness of quantum computing. We're also part of the efforts to develop a workforce through some of these engagements here, through me being here, things like this. We work with the Potomac Quantum Innovation Center because our ability to make use of these technologies will rely on lots of people capably doing it. So quantum computing, developing realistic metrics. Some of the current metrics are to understand quantum volume as the ability of a quantum computer to just sort of run a bunch of gates in a circle or in a square in this case, and just keep running them until they fail. But that's not a real quantum algorithm. The other one is just to measure qubits and depth, gate depth, or Toffoli gate depth. But that doesn't account for error. So we want to account for both quantum volume, qubit number, error. We want to be able to incorporate all of those into a single metric. And so MITRE has developed a quantum volume metric that does incorporate both number of qubits, gate depth, and error. And we call it our quantum volume, V sub q. We can actually plot the V sub q of the quantum computing, the quantum computers' trajectories. It's a little bit starker than I think I'd like, but all of this is based on the fact that we do not right now have fault-tolerant quantum computing. So that line, I would like to see everyone in the room think about, consider how you can steepen that line. If we can steepen that line by developing fault-tolerant quantum computation, we will get up there towards machine learning, materials discovery.
Not the right time for the question.
No, it's questions as they come.
So, have you made a version of this where you can IonQ's use projections? Because they're very rosy and optimistic about the future.
Right. So they're saying one of their projections planned, their log sub q of their projected quantum volume as we evaluate it is 1,000 by 2028. So they want to be. Let's see. Can I do this?
They're definitely.
How do I get my laser?
Oh, it's on. You see those circles on the bottom?
Yeah.
The third from the left. Okay.
Got it?
Yep.
So over here, they want to be 2028, 1,000. They want to be around. They want to be here. Based on their projection. So
I don't remember how they want to scale beyond that.
that would be nice if it would be nice if this was wrong.
Yeah.
Yeah. I didn't make it, so I would be okay with it. So how and whether to get into a quantum career at MITRE or anywhere else. Do I have much time left? Good. So I think the answer is yes, there are jobs in the quantum industry. Billions are flowing in, and this should just be the beginning because we have a lot of work to do in many aspects of quantum technology, quantum computing, quantum sensing. Quantum sensing is near term, in my opinion, and in the opinion of a lot of people working in that space and our sponsors' opinions. And so there's money flowing in, there are jobs, they pay well. And the skills are transferable across the ecosystem. If you understand how to build and control a qubit for quantum computing, you can just move right over and do quantum sensing. So the way it's been framed is that in the quantum industry, hiring is not limited by funding, it's limited by potential applicants. There are 3 jobs for every applicant in the quantum world. So the jobs are there, they pay pretty well. And the ways to get into it are, you can actually get into it right away with a bachelor's degree. Historically, it has been said that the professional degree in physics is a PhD, and that is just no longer true. As the quantum workforce the quantum ecosystem needs its workforce, and it needs its now. And they are hiring bachelor's degrees, training them as technicians, and many times often paying for their master's degrees. So you can get started right away with a bachelor's degree and experience no gap in lifetime earnings for a quantum industry that's increasingly hiring at the bachelor's level. You can get a master's degree. It takes 1 to 2 years plus tuition because a master's degree is not paid for the way a PhD program is. But again, if you go into the workforce, your employer might pay for it. Master's degrees, they can augment your experience and your knowledge fairly rapidly. They're a good augmentation on hands-on experience and can then make it easier to find jobs in the quantum industry going forward. You look in sort of the job requirements, oftentimes in a preferred candidate, they would list master's degree. So you don't need it. Your abilities are more important, but sometimes just smooth out the process. It's not a terrible idea, but again, all of these are viable. All of these are good. The last one, doctoral degree, 5 to 7 years of hard work, low pay, or you come out of it prepared for a quantum job with autonomy and leadership. You can be, with a PhD, the PhD is trained to be a research leader and to be able to autonomously pursue research endeavors. And physics PhDs have historically low unemployment. So even in the 2008 recession, employment, if you include that, it's still less than 3% unemployment. So it's a very hireable degree for the quantum workforce and other things. So with that, I'll end my talk and take any questions. They are. MITRE has a significant effort in cryptography, cryptographic engineering. Yes. That is, I think we were talking about earlier in Patrick's talk, the question of what do mathematicians get hired for? And the answer is algorithms, but it's also cryptography. And it's also actually sensing, because when you get bombarded with all of this sensing data, mathematicians are often the people that are going to figure out how to turn that into knowledge, how to extract useful parameters from the sensed data. A hand up there. That's a great question. The answer is probably yes, but it would be hard. So we have to do public release for things, and our sponsors, our government sponsors, would have to allow for those releases. So we do that for our government sponsors, and some of those get publicly released. And can you email Patrick, and I will email Patrick. So I'll find this information for you. It's both. It's a private, not-for-profit company, and it wins contracts to do work for the government. So,
Or are you kind of unique that you only have?
somewhat like that. We generally don't even have to compete for the contracts we win. MITRE just wins them outright. And yeah, so we don't compete for them, and when we do, so there are lots of organizations that operate federally funded research and development programs. And they all have somewhat their own expertises, so they don't overlap so much that we're competing with each other. We're mostly just doing our thing, leaving each other alone, or where it makes sense, we work together. So MITRE often works with MIT Lincoln Labs. MIT Lincoln Labs is a federally funded research and development center, and they're focused much more on science and technology. So it's in the early stage research, and MITRE is a systems engineering company. So we don't just focus on the technology, we focus on how the technology is a subcomponent within a larger system and have to accommodate the various inputs and outputs that need to work within that system. So we can work well with MIT Lincoln Labs while not stepping on each other's toes for finite resources. No, yeah. So does that answer the question?
Yeah.
Yeah, so it's a great question. And one example of someone who came straight out of PhD is from Patrick's lab, Sean Oliver. The day-to-day is interesting. I spend about half of my time doing research, hands-on research. I work on the quantum diamond microscope project that actually Patrick leads. Yeah. I'm sorry, not Patrick, Sean from Patrick's group. Entanglement. Yeah, so Sean Oliver from Patrick's group leads. I get to spend about half my time developing that technology, developing instrumentation, and advancing that capability. The other half of my time I spend doing more quantum materials research. I actually spend a lot of time doing hands-on research, and then a little bit of time answering questions that relate to what is this emerging technology, how do we forecast its eventual usefulness, how will it be useful for this sponsor in this application space 3 to 5 to 10 years out. So it's a combination, for me, a combination of lab work and kind of writing white papers about technology. So I don't do the work, I'll do research papers to answer those questions. So people coming straight out of undergrad or grad school would probably do more of the latter at first, is take their ability to understand emerging technologies and the underlying science, and then use them to answer questions of their forecasted usefulness in certain applications, in certain operating environments, sometime. But eventually, many of us, one of the reasons MITRE hires people like us is they want people with that kind of expertise and the ability to understand these problems but it's really hard to get people that never want to go back into the lab. So we find lots of ways to get back in the lab while we do that. And it maintains our expertise, it maintains our contributions that we want to continue to contribute to research. So MITRE is a